Before becoming the father of the atom bomb, J. Robert Oppenheimer contributed to black hole research. For better or worse, Oppenheimer will always be identified with the atomic bomb and the mushroom cloud, a near-biblical symbol of annihilation. Oppenheimer, Christopher Nolan's biopic of the scientist, premieres today, July 21. Oppenheimer was a quantum physicist before going to Los Alamos, New Mexico, in 1942 to help build the atomic bomb. In 1939, he and his University of California, Berkeley colleague Hartland S. Snyder wrote on continued gravitational contraction, which used general relativity equations to show how black holes may be produced. Oppenheimer proposed the very first collapse model to describe how a star could collapse into a black hole. Xavier Calment, a physics professor at Sussex University in England, told Space.com. This concept explains black hole generation as a dynamical astrophysical process, the final step of heavy enough star evolution. This model is still utilized. Ironically, Einstein, the father of general relativity, was finishing research to prove that black holes did not exist when Oppenheimer and Snyder worked on the paper, which relied largely on it. Another theoretical physicist pondered star collapse and black hole genesis 8 years before Oppenheimer's idea. When this fuel is out, a star collapses. The star's core rapidly contracts, leaving an unusual stellar remnant. Mass of the stellar core determines remnant type. Indian-American physicist Subramanian Chandrasekhar discovered that quantum processes prevent particles from squashing too close, stopping gravitational collapse in star cores with a mass less than 1.4 times the Sun. For stellar cores at least 1.4 times more massive than the Sun, gravitational collapse generates enough pressure and heat to trigger nuclear fusion, which forges heavier elements like nitrogen, oxygen, and carbon from helium. The largest stars collapse and fuse several times. Oppenheimer and his students sought to discover where this gravitational collapse path leads and what happens to the universe's greatest stars. Astronomer Karl Schwarzschild received Einstein's general relativity theory in 1915 while serving with the German troops on the front. Schwarzschild calculated an accurate mathematical solution to the general relativity field equations under these extreme conditions, shocking Einstein. These solutions contain two alarming singularities, where physics breaks down totally. These singularities suggested things with strong gravity may swallow light. Mathematical modification could remove a coordinate singularity. The Schwarzschild radius, the point at which a body's gravity is so strong that the velocity needed to escape is more than the speed of light, is this coordinate singularity. The genuine or gravitational singularity was unsolvable mathematically. The black hole's heart, where physics breaks down, was and is unremovable. That was the theoretical birth of black holes, but it didn't say anything about their genesis. Oppenheimer investigated how black holes could form while Einstein worked to abolish the gravitational singularity in 1939. Oppenheimer gave Snyder simplistic assumptions that ignored rotation and quantum phenomena. This paid off when the latter researcher found that a collapsing star's appearance depends on the observer. Snyder hypothesized that light from a source near the event horizon would redshift as it moved away from the collapsing star. The observer's frequency of this light is decreasing. This frequency reduction continues until the distant spectator sees the light frozen. Oppenheimer and associates discovered that the scenario changes for an observer falling with the collapsing star. This observer would fall past the event horizon without noticing. Naturally, an observer would be spaghettified by intense tidal forces induced by the difference in gravitational attraction on their upper and lower body. Smaller black holes with Schwarzschild radii near to the gravitational singularity would die before hitting the event horizon. Due to the apparent freezing of light at the event horizon, this concept was initially called a frozen star. John Wheeler, a Princeton University physicist, invented black hole in 1967. Oppenheimer and colleagues took a different route than Schwarzschild, but they arrived at the same idea: a gigantic stellar body that traps light and creates infinite redshift. Oppenheimer and colleagues were the first to understand black hole birth. Schwarzschild had the theory. 3 years later, Oppenheimer visited Los Alamos, cementing his position in history and popular image. Black holes are his legacy, especially among physicists.